Good morning, angels.
Good morning, Vincent.
Rookie, are you settled in?
Okay, I guess.
Good to hear. Angels, we have a new case.
That works.
Are you familiar with lipid metabolism?
Sure, it's a metabolic process involved in the breakdown and synthesis of lipids.
However, we are going to focus on de novo synthesis of lipids.
So basically, our mission deals with the creation of fatty acids by the body.
Your mission is to receive the acetyl CoA molecules.
Good.
Really, Ricky? Really?
Hit you with it. Just hit you with it.
Don't get the rookie. Um.
This is where you see mission is our goal. Angels, let's go. So, who is going to retrieve the acetyl-CoA?
Rookie, as expected.
No. The only logical way. Rock, paper, scissors. Okay, go ahead.
Lizard Spark!
May the force be with you. Good. Ready? 1, 2, 3.
Isn't it obvious, Ricky, which door you should be checking?
What is the acetyl coenzyme A molecule?
Well, acetyl-CoA is an important molecule in metabolism. The main function is to act as central intermediate of the pathways required to metabolize non-fermentable carbon sources.
The structure of acetyl-CoA is unique in that it consists of a carbon acetyl group, which is attached to a coenzyme A. Coenzyme A, in turn, consists of three parts: a beta-mercaptoethylamine, a pantothenic acid, and a 3,5-adenosine diphosphate.
It is also the first molecule involved in the de novo synthesis of fatty acids process.
Hold on. What did you say that it was doing with the fatty acid?
You know de novo synthesis of fatty acids? De novo meaning a new, synthesis meaning making, and fatty acids the building block of fats in the body. Therefore, it is the making of fatty acids from the beginning.
When would our body need to make fatty acids?
When there is an excess of carbohydrates, proteins, and other molecules in a body after a meal.
And this helps in the buildup of fats in the body. So you see, not only fatty foods cause you to be fat, it can also be the amount of foods eaten by the individual.
So this acetyl coenzyme A molecule is found in the mitochondria and made by the oxidation of pyruvate. However, because the coenzyme A portion of the acetyl coenzyme A cannot cross the inner mitochondrial membrane, it must enter the citric cycle where it is converted to citrate via the condensation of oxaloacetate and acetyl coenzyme A.
The citrate then enters the cytosol where it is converted back into oxaloacetate and acetyl-CoA. This is done by the enzyme of citrate lysase and by the addition of CoA. It is this cytosol acetyl-CoA that is used to synthesize fatty acids.
The first step of the synthesis of fatty acid is the commitment step. This is when acetyl-CoA is converted to malonyl-CoA by acetyl-CoA carboxylase, which is the regulatory enzyme. This is said to be the commitment step because after the acetyl-CoA is converted to malonyl-CoA, it must be made into the fatty acid molecule and cannot be returned to the citric cycle.
But how does 2-carbon molecule convert to a 3-carbon molecule?
This is because the enzyme acetyl-CoA carboxylase uses a cofactor called biotin. Biotin is a chemical compound that is required to activate the enzyme that it is bound to. In the presence of HCO3-, a bicarbonate, and ATP, a COO- group attaches itself to the acetyl molecule using the ATP provided.
Biotin is a bifunctional, meaning it has two different functions with two active sites, biotin carboxylase molecule and transcarboxylase. The first biotin carboxylase catalyzes the addition of COO to the biotin molecule by hydrolyzing 1 mole of ATP, and because of the lye side arm, it swings to the second active side, transcarboxylase, where the COO is added to the acetyl-CoA to form malonyl-CoA.
This newly formed malonyl coenzyme A goes through a series of reactions catalyzed by a multifunctional enzyme called fatty acid synthase. This enzyme is a large protein with 7 different active sites that are able to work on their own. However, using fatty acid synthase, only a 16-carbon fatty acid is made. The fatty acids it produces must be of an even number and saturated.
Fatty acid synthesis occurs in a cycle, and in every cycle it adds 2 carbons to the chain. The first step involves malonyl-CoA and acetyl-CoA, but only the first step. Elongation of the fatty acid only involves malonyl-CoA.
There are 4 steps involved in the elongation of fatty acids. That is condensation, reduction, dehydration, and reduction in that order. For every cycle, 2 NADPH is oxidized.
The fatty acid synthase complex consists of 2 attachment points. These are the SH group of the cytosine residue in one of the several proteins and the SH group of the acetyl carrier protein. This reaction involves the acetyl group of the acetyl-CoA molecule, which is transferred to the cytosine SH group and to be catalyzed by acetyl CoA ACP transacetylase. The second reaction involves the transfer of the malonyl group from malonyl CoA to the SH group of the ACP. This is catalyzed by malonyl CoA ACP transferase.
There are 4 steps involved in the elongation of fatty acids. That is condensation, reduction, dehydration, and reduction in that order. For every cycle, 2 NADPH is oxidized.